Design a key value store. Hi everyone, we're here today for another Exponent mock interview with Andreas. All right, thanks so much for being here with us today, Andreas. Would you introduce yourself quickly for our viewers?
Hey everyone, it's great to meet you. I am Andreas. I'm a software engineer at a mental health startup called Modern Health.
Okay, awesome. Thanks so much for being here. So let's get started. Our question today is design a key value store.
Awesome. So I guess I'll start with some clarifying questions. Does this key value store need to be able to support updates?
Yes, you should be able to update, add, and delete.
Okay, great. Here, I'll share my screen as well as I take notes during this. Okay, so we need to be able to update and delete. Awesome. Okay, great. And then, so how many queries per second do we need to be able to support with this store?
It should be a lot, as many as like 100,000 per second.
Okay, great. 100,000 per second queries. And can we assume those will be both read and write?
Yes. Mm-hmm.
Okay, great. All right. And will we be hosting all of this data in a single host or multiple hosts?
For now, let's just focus on the single host use case, but it should be designed so that it's easily extensible.
Okay, great. Awesome. And so I guess now that we have some of those clarifying questions answered, I'd like to maybe get a sense of the scale of the system we're going to design as well. I know I asked about the queries per second, but in terms of the data, how much data do we plan on being able to store?
We can assume that it's a pretty large system, so handling some of the biggest data stores today, so on the order of terabytes.
Okay, awesome. So I guess to dive into that, so if we can assume terabytes, then maybe we can have like around 5 terabytes per like node in our system, where, you know, let's say we run like 1,000 of these individual nodes. So that gives us total of something like, what is that, 5 petabytes of data. And we could always increase that, I guess, in the case that we do want to add additional hosts or expand our data set. But hopefully that'd be able to, it can, you know, have enough capacity for what we want to be able to store.
Mm-hmm. Okay. And what are the differences between what you have written here, nodes versus hosts?
So in these versus hosts?
Nodes.
Oh, nodes. Yeah. So I think essentially, yeah, we can assume maybe those are nodes are individual groups of data stores. And so we can have on a host, let's say, yeah, we'll have, actually, we can assume that it'll be 5 terabytes per host. And so in the entire data center, I guess, we could have a total of these 5 petabytes for the whole system, if that works.
Okay, sure.
Cool. And then in terms of like the key values individually, how much can we, maybe we can assume like there's a limit of like 1 megabyte for each of those. How does that sound?
Yeah, that sounds good to me.
Okay, great.
So that's for a single key value pair, right?
Yes, for the each row of data, I guess, within each of our tables.
Okay.
Cool. So given that we have a bunch of these characteristics, do you feel ready to, I guess, for us to move on to talking through characteristics we might want to support in this?
Yeah, that sounds good to me.
Awesome. So in ranked order, we're probably going to want to look at durability. So actually, I'll title this Characteristics of Our Data Store. We'll want durability, and in the case of durability, I think this will be the most important because we never want to lose any of our clients' data. So I imagine that is probably the chief job of a data store.
Yeah.
On top of that, we'd like availability. We can say is one of our chief characteristics as well, but it's not as important as durability. We're okay with returning things slower rather than not being able to return that data at all.
Yeah, that makes sense.
Awesome. And then finally, performance. And in those cases of performance, just being able to still have optimal performance, but these two other characteristics would go above it. And then finally, I guess to make a note, for the simplicity's sake of our system, maybe we won't handle security on our system. That we can assume our clients will handle encryption of data and all of those aspects, if that's all right with you.
Yeah, I would say that's not within scope.
Okay, great. So from there, I guess we can start thinking a little more about another characteristic of our database, which I think in this case we'll want a strongly consistent model. And this is because we're developing a distributed database, we'll probably want to be able to make sure that we're returning the same thing every time for each of the pieces of our database. And so in this case, we don't care about, although we put availability as one of our priorities, we'd rather have it highly consistent than highly available, so that we can be able to have reads as a result of our successful write operations. And in this case, I think because we are going for strong consistency, we're not going to be able to support ACID properties. In favor of consistency, we can't be able to assume that we have the A for atomicity, or the I for isolation. In terms of atomicity, as you probably know, we can't send like 5 requests to the database and then all of them execute at the same time. In that case, or none should be executed, because we want to make sure that in the database we are having that consistent data, that where someone sends it, then we're making sure to store it. And then in terms of isolation, we're not going to handle any sort of locking at the table or row level, but I'll be able to, I guess I'll talk about that a little later, of how we can have a compensation for that practice with how we choose to store our data, to make sure that we still do, whenever there are conflicts, there will be a resolution for that.
Yeah, okay.
Awesome. So these are some of, I guess, the basic characteristics of our database, but maybe we can talk about some operations that we want to be able to support with this store. Does that sound all right for you?
Yep, perfect.
Great. So what operations do we have? So our DB is basically a bunch of tables, and then each table has a key and value record, which is pretty much, I guess, how a lot of databases operate, although there are some different ones. In this case, we'll also want a sequencer attached to each of those key and values. And in this case, the sequencer will just allow us to be able to determine not only which time that those rows were added, but in what order. And that will help for things like the conflicts. And I'll talk about that in 1 second, but take us through at least all of the basic operations before we get to those edge cases, or, cases we want to make sure they account for, but are not the initial, I guess, design. So in terms of our operations, going back to what we specified before, we want update, add, and delete. So in terms of that, well, first of all, we're going to want to be able to create tables in the database. Second of all, we'll have put, as we talked about. And so that'll take a key and value. Third of all, we'll do get, which takes a key, and then we return the value. Fourth of all, and delete. That's right, we have delete there. And update will take into account with the put operation as well. And I'm trying to think, what else do we need? So we have put, get, delete, create table. We'll probably want to list all of the existing, if we want to list all the values in sorted order, and we can do that.
Sorry, is it listing values or listing keys?
Oh, right, listing keys. Thank you for the catch. And so we could have delete table as well, since we already have create table. But I'll leave that as just an optional thing. But obviously it would be beneficial. So back to the sequencer. So what is a sequencer? Talked about it a little bit, but digging down deeper into it, sequencer will have a timestamp, which is, in total, it'll be around 16 bytes of data, but we're going to have a timestamp right here first. And that is going to be 8 bytes of data. And then we'll also, I'll scroll down. We'll also have a unique number per node. So by node, I'm meaning in this case host, as we talked about before. So I'll just refer to it as host from now on. And then a unique node ID. So that's unique to all the nodes. And we can say that is also going to be 4 bytes. And because it's 4 bytes, that's around 2 to the 32 possible, 2 to the 32 possible numbers, which should be enough given our system design, how we were talking about before. So that leaves us with, 16 bytes for every key value, which puts us far under our 1 megabyte limit. So we should hopefully be good.
Yeah, okay. So a quick clarification. So it's a single host solution in the sense that each value can only be stored, does not need to be stored across multiple hosts, right?
Yes, exactly.
So we have multiple hosts to support the entire data store.
Yes, exactly.
Okay, yes, that makes sense.
Yeah. So they'll each be individually located, and I guess in the case that we want to then locate where they are, which I guess we'll get into later, then we'll need to know which unique host they belong to in that case.
Okay, gotcha.
Cool. All right, great. And so I guess there's, we talked about the edge cases. The ideal case is this all works out and we have, let's say we have a put of 1 or A, and then the value is 1. And then we have a get of that. Everything should work smoothly when we're doing that. But if we had 2 rapid in succession, let's say we had a B2, and then right after that, someone almost instantaneously did B4, how do we reconcile these two? So in that case, how we're going to handle these collisions is using the sequencer, we can determine which put got put in first, and then we would prioritize the one that got put in first as the source of truth. So since we're running that in a distributed system, that is a possibility, and we're not doing locking, we're going to resolve to, not the first one, but the second one that would have been put in to be able to handle that behavior, I guess.
Mm-hmm.
Does that seem all right to you?
Yeah, that makes a lot of sense.
Great. So now that we can reconcile those two, and that was an example edge case, maybe we can move on to the overall structure of the of our system, since we have kind of a sense of the operations and what we're wanting to store here. Okay, so overall architecture, let's do it. So we're in the system. So our overall architecture. Boom. So we've got this overall architecture. And to start, we're probably going to need to receive requests from a client. So we can just call that a request manager. Actually, use this, and we'll have a request manager here. Great. So this request manager, we can consult a metadata manager, which is which essentially allows us to figure out. Metadata manager is going to be able to handle what parts of the system we need to refer to. Those it's really relying on those sequencers we talked about earlier, and it's coordinating and orchestrating where we're putting in new keys and which nodes it should go to. And assuming we have these individual, I guess we can call them replication groups, where each of those are going to have a leader and then 2 nodes that are followers. I'll go into those once I go into those replication groups a little more. Our metadata manager is essentially creating a mapping of all these replication groups and handling, if one goes down, if the one leader, for example, goes down, move another follower into the new leader's position, and also taking in requests from the request manager and mapping it to the correct place. In this case, go ahead.
Oh, no, I just said okay.
Oh, great. And so I guess in those cases, there's actually a lot of tools we could use for that. From what I know of, Redis and Zookeeper are 2 popular ones that we could use. I would lean towards Zookeeper because it has a lot of built-in functionality to be able to support something like this, whereas Redis would take a little more customization and work to get it up and running for this. So does that seem all right to you, that we're going down that path?
Yeah, so all of this metadata that's storing, is it storing all of that in memory?
Okay, so in this case, Zookeeper would, yes, keep all of this data in memory about all of these, where they currently exist, and be constantly updating and backing up this data, so that, because that would be so critical of where the request manager is wanting to send those requests to. That's a great point. And then from there, so I referred to this as one request manager, but since we're building a distributed system and we're handling 100,000 requests per second, which is a lot. Yeah. So we have this request manager. We're probably going to want a lot of them all here in a distributed manner. We're going to need a load balancer across these. So, as always with load balancers, I guess it's important that we think about how do we want to distribute load across whatever we are, distributing load for. And in this case, our request managers. To do it so evenly, I would think we could use just a least traffic sort of algorithm. So we could direct traffic to the request manager that's processing the least requests at the moment. And then that one would be able to interact with our metadata manager.
Okay, yeah, perfect.
Great. So we have this load balancer, we have request manager, we have metadata manager. Now we're sending requests, we know where they need to go. So let's send them where they need to go to, I guess, in this case, going back to the replication groups. So I guess in the case of the replication groups, we have metadata on where we need to process information, and the replication groups, I guess I would describe that as, here, I'll write this here. Replication groups, in this case, I would describe as being in charge of a certain part of the table. Each individual portion would be in charge of one, like let's say we have A to Z. Here, I'll write here. We have A to Z different keys. And as our example we were putting before, A and B. Then we'll have one replication. We'll have, let's say, split it into three. We'll have one replication group that is A to, I think, F or something like that. F to R, and then R to Z, generally. Just assuming, I guess, I don't know, A to F may have like a lot of frequency of words. So given that, we'll send this data to the replication group, and we always would want an odd number of nodes. This is so that in the case that when we always want one leader, and then that leader will be able to dictate like which method of consistency that they want to vote on or decide on. That's probably getting a little into the weeds, but I think that would, in our case, we can just assume, I guess, 3 or 5 of these individually. So given that each of these nodes themselves are comprised of like a log that they have all of the individual operations applied to them, and then also a B plus or LSM tree that will be allowing us to index each of those. And since we're doing both reads and writes, but a lot of modern systems are leaning towards heavy writes, LSM tree would be beneficial. In this case, I'm thinking rather than B plus tree, but I guess I would leave that to you. Do you think we would want to do, what is your opinion direction we should go?
Yeah, that makes sense to me. Could you give a quick explanation of what an LSM tree is?
Yeah. So essentially, it's a tree that will allow us. It's like similar to a lot of other algorithms that'll allow us to be able to sort and index all of the individual nodes and keys within our system, so that we have quick access to them, and similar to like a hash table or something like that, where we could quickly and consistently access these different nodes in the tree, rather than having to go through and individually, like, n times sort through and find wherever we need to write in the table.
So why is it better for writing than a B plus would be?
Yeah, so in the case of, I think specifically, LSM trees lean towards write-heavy systems because they work. I'm not sure. I believe it is because they work on the way back versus they are working pre-computing and doing it on the way there. So for write-heavy systems, they are leaning towards stronger consistency on the write side when they're finding the individual node and then making that write operation. And on the read side, you would just be looking for the individual values and then routing to those.
Yeah, and for the writing, you optimize it by performing only sequential writes in an LSM tree, right?
Yes.
Yeah.
And so from the request manager, I guess we have this replication group. We have each of the nodes within those, and I can talk a little bit more about the replication groups, which I talked about that there's a leader and then 2 followers, and they'll each talk to each other. So the leader will send a message to each of the followers saying, all right, I just got this operation, after they perform it. Kind of like on a plane where someone, you put on your mask first and then you help other people put their mask on.
Yes.
You would do the operation yourself, do the get, and then pass down the message to the person, to the followers next to you. And so those followers try to stay in sync with the leader. And the leader will wait for one of them to be able to send a response back after it completes the operation, sending that an okay response. And once the leader sees that there's an okay from one of the followers, then the leader will send a response all the way back up to the request manager, is that, okay, we completed it. I guess the benefit of this model is that if the leader goes down, we'll also still have a copy, and then one of the followers can become the new leader, and that would be handled by our metadata manager that would be able to keep track of all the leaders and how they're doing and their health, I guess, in this case. So we have these replication groups with leaders, and finally, we're going to be able to need to, I guess, monitor all of these, but monitor them not for in this case, the health of the leaders, but monitor them overall of how, like, are they becoming overworked? Are the tables individually becoming too big? Because we have decided to parse each of these groups into representing parts of our table, or where one is A through F. Like, let's say we're just getting a ton of keys that are A through F. We'll probably need to actually split this into a couple of different groups, and that's what we'll call it our controller will do.
Okay.
So let me create a controller here. Great. And this one, the request manager will talk to it, but then also it will monitor the replication group. Actually, I'm not sure if it needs this. We'll just say that. Okay, great. So we have this controller that's watching all of these tables, and essentially like large, I guess I could go into it deeper, but this controller, this main function is being able to monitor all of these, and it would split this A to F into, let's say, A to C, and then this one would be D and F, if those were getting overworked.
Mhm.
And that gets complex. I don't know, would you like me to go into that? I feel like it might be a little out of scope for this, but what do you think?
That's okay. Maybe just a high level quick summary would be great.
Okay, great. So we have this A to F table, and essentially we have a bunch of rows, and we would find the point at which it's usually about a halfway point at which those two were getting filled up with additional reads and writes. Controller works with the metadata manager to be able to understand where the current location of all of these are. And then the controller would say, okay, let's coordinate establishing a new leader, and adding in, it has like a pool of nodes, and it takes from those pool of nodes and then would add them in to be able to create a new table that is now two separate tables representing this larger table, similar to how we've already had for D to F and F to R, R to Z. So we could continuously split off into additional tables to continue to scale as we needed if there were hot zones within our table information data.
Great. Yeah, that's a good point.
Cool. So yeah, I think that's pretty much it on my high level design.
Okay, awesome. Yeah, I think that's a great place to pause as well. You did a fantastic job. Yeah, so I think it'd be great to do a little quick debrief now. What did you think of this interview? What do you think you did well, and what do you think you'd want to work on more?
Yeah, definitely. I think I didn't have as much familiarity with the key value store, but I tried to go back to some of my just system design principles of trying to ask a lot of clarifying questions, understand what we're building, and think through the process before I actually get into the architecture design. I definitely felt I struggled a bit with some of the getting down to the nitty gritty of like, I remembered definitely aspects of like the replication group, but I didn't remember like the log and what sort of how we want to store them. But for the life of me, I couldn't remember what the LSM tree, like how it worked and operated, but I did remember it was write heavy. So I probably would have studied up more on that.
Yeah, I thought you did a fantastic job with starting your design from first system design principles, and I always recommend that as a way to go if you're not entirely sure where to start with a system. Yeah, so you did a great job, for example, of considering some of the bottlenecks in the system, like what happens with certain hot zones, like if there's more keys in a particular replication group, or if it's like expanding faster, like what do you do? I really like that you considered that. And I also really like that you mentioned which specific aspects that you were optimizing for. So you were prioritizing consistency, even though that meant that you might not be able to fulfill all of the ACID properties, but you gave really good justifications for that, which is great. Yeah, and I also like that you were careful to consider a lot of the edge cases that could happen. Like, for example, like if you have collisions, and those are all really like thorough, detailed considerations that are great to include in a system design interview. I think, yeah, a couple of the things that would have been helpful to hear about a little bit more, as you mentioned, like LSM trees versus B plus trees, perhaps, though you don't necessarily have to go into detail. I think of it like high level summary is already sufficient. And another thing is maybe talking a little bit more about the health monitoring system. Because you mentioned a little bit that like, if the leader goes down, then we want to replace it with one of the followers. But how exactly do we know when the leader goes down? Is there some sort of like heartbeat like monitoring system?
That's a
Yeah.
great point. Yeah, I think that would have been good to include, but thanks, I appreciate that feedback.
Thanks. You did a fantastic job today, Andreas. Thanks for joining us. And for those of you who are watching at home, good luck on your upcoming interviews. Bye.